In this work, we introduce decision-making for human-in-the-loop robotic agent via uncertainty-aware reinforcement learning. Human-in-the-loop robotics is a paradigm where a robot is acting autonomously most of the time, but is occasionally assisted by a human operator. This powerful paradigm is seeing increased usage in both academia and in industry. However, a key limitation of this approach is the inefficiency of human assistance. Human assistance is usually time-consuming and expensive. Previous work usually assumes to call humans assistants in a greedy manner, or let the human decide when to intervene the robot. However, a robot should make decisions of whether call for humans assistance to genuinely achieve the autonomous goal. The problem of when to interact with humans for learning agent is underexplored in robotics. In this work, we explore the feasibility of using reinforcement learning to optimize the use of a human agent. The key idea of our work is we want to optimize a human-in-the-loop agent to call the expert as little as possible. We present Hula for human-in-the-loop uncertainty-aware learning agent. In our framework, the robot decides when to call the operator for assistance. Specifically, we propose to use uncertainty as metric to make this decision. In this work, we use variance of returns to quantify uncertainty, since it gives direct information about whether the agent is uncertain about its outcome in terms of task performance. Building on Q-learning, which learns an estimate of the expected return from the current states, Hula additionally uses Bellman-like update rules for variance estimation. This is similar to Q-value estimation. During deployment, a Hula agent asks for human assistance if the estimated variance is higher than a threshold. A key feature of our approach is no expert call during train time. This makes training efficient and do not make any assumption about the form of assistance provided during deployment. To validate our method, we test Hula in environments that have high uncertainty. For example, in this environment, we add stochasticity in the transition function using action errors. For each commanded action, there is a 40% chance that a wrong action is executed. There are also several traps in this environment too, so action errors can result in states with negative rewards and end the episode. These emulate action errors that can result in unrecoverable failures during robot deployment. Our results show that our method effectively captures the uncertainty of a trained agent. More crucially, during deployment of this agent, our method calls for experts' help when it is close to obstacles, where action errors can lead to task failures. In the next experiment, we investigate how our method performs in partially observable environments. In this environment, the agent is provided only the top-down 5x5 windows as observations. These impartial observations limit the agent's ability to localize itself in the map and to produce correct actions that reach the goal location. For example, the observations from the entrance of two passages in this environment are identical. However, different actions should be taken in these two states. Our results show that a Hula agent can assign high uncertainty when the agent has difficulties to localize itself. When it encounters confusing states, the learned variance is higher than the threshold and it decides to request assistance from an expert. When the observations allow the agent to localize itself, the Hula agent executes its own policy and does not consult a human. Finally, we compare our results with a penalty-based agent. The penalty-based agent extends the action space with additional expert calls. This allows the policy to reason about the effect of human assistance during training. Our results show that the Hula agent reached similar performance as the penalty-based agent. Both performances are better with more expert calls. However, the penalty-based agent calls the expert during training many times to achieve this similar performance. This training is not scalable for practical robot learning systems, whereas our approach do not require any expert call during train time. Also, The penalty-based agent makes its own decision to call the expert in a greedy manner to improve task performance. Hence, it is hard to adopt it with budget of human interactions. Our method can be used with different expert call budget by setting different variance threshold. In conclusion, in this work, we investigate the decision-making of when to ask for human assistance using uncertainty. Although our work is limited to online RL, our ongoing work extends HULA to offline reinforcement learning, which allows us to learn uncertainty-aware agent using offline data. In the future, we would like to explore more axes of human-in-the-loop policies. For example, which part in the observation causes confusion, how to ask for human assistance, and what can a human provide for assistance. Thank you for watching.